Welcome to the Tech Talk today. I'd like to introduce our speaker. This is Andre Alexandrescu. I got it right. Cool. He's here to give a talk on the D programming language.
Thanks, Benjamin. It's a great honor to be here. Thanks very much, Benjamin, for inviting me. And thank you all for attending. I have to admit I was quite a bit insecure about, my threshold was 6 people, and I'll tell you exactly why. I thought if 6 people are not going to show up here, it's going to be an embarrassment. I'll tell you exactly why right now. I have this food locker here. All right, so I have this book. And this book has no author on the cover, right? Has no author. So that what happens is in the world, there are 1,824 copies of this book without an author on it. The rest do have the author name on it. And 1,824 plus the 6 I have in this bag. And I'm going to give away 6 books for the 6 most embarrassing questions that you're going to ask. All right? So get ready. Embarrassing to me. All right. And I'm going to keep this microphone on hand. So if you have questions, I'll give it to you. All right. I've given in the past talks about sort of the dog and pony show about D, and I changed my mind this time around. I decided to go with 3 cool things about it. I'm sure many of you have heard of D to some extent. Most of you are going to find it familiar if you use C or C++ or Java. And therefore, I'm not going to go through the sort of garden variety of features that D offers. Instead, I'm going to focus on 3 things. First off, how many of you are using, for example, C++ in their day-to-day work? All right, Python could be could be an intersection there. Okay. Other languages? All right. What languages? Talk to me. Java. Okay, Java. So let's take a vote on Java. All right. Perfect. Erlang. Anyone? Erlang. All right. So what's the deal with D? Oh, this is starting to play here. All right. So the programming languages landscape as of 2010 has a lot of languages plastered all over it. There are systems languages, there are productivity languages, there are imperative, functional, declarative languages. There's this generation system that, fourth generation language or whatever didn't really catch on. I heard of it in the 80s, but it seems to nobody cares about it. And there's compiled versus interpreted versus jitter languages and so on. Now, part of the territory has been charted, and there's this very nice chart made by 2 Russians, in which there's this C++ lands with all this good stuff here, and I turn out to have a castle over there, which is very convenient. I also have a ship, Loki. And there's also, the boost territories, and there's terra incognita and all this fun stuff. I find the chart very, very nicely done and very funny. But in the middle of this chart, there's a Sahara-sized desert around the crossroads of a few desiderata that nobody's occupying right now. So you have this program, PL landscape, that has a huge unoccupied area. And the huge unoccupied area is at the intersection of the following good things to have. The good things to have are we want high efficiency, we want systems level access, we want huge modeling power because we have difficult problems to solve, we want simplicity, we want productivity, and we want code correctness. And last but not least, we want correctness of multi-threaded and concurrent and parallel code. So the question is, which language occupies this area? It's no man's land, really. So traditionally, what languages have done, they focus on a few of these and try to kind of keep the others in control. Like, for example, I don't know, Python is a beautiful language, so I think it ranks high on simplicity, it ranks high on productivity. It doesn't rank very high on, for example, efficiency or systems level access. And I'm afraid it doesn't rank high at all on parallelism. I think, does Python still have that one global lock that everybody locks? Okay, I think it's terrible, right? All right. C++ is the undefeated ruler of 1 and 2, high efficiency systems level access. It's stronger on 3 than C, has high modeling power, but it fails miserably after that. Not simple, not productive, and code correctness is at least 10 years. So D takes a holistic approach towards the centroid of this territory. So what we want to do in D is, you know what, so there are these wishes that everybody could have about the programming language. And essentially, we don't want to focus on a couple and forget the rest. What we want to do is try to holistically approach everything and try to find the best compromise across all of these dimensions that are contradictory to some extent. I mean, think of this. Modeling power and simplicity don't go well together, right? They don't sit well, right? All right. A few basic things about D that I think are interesting. Yes, question? Why doesn't modeling power and simplicity go well together? Why does it not go well together? In my opinion, I think a language with good modeling power will have to have quite a few features, what people call features. They have to have good privacy control, for example, good visibility control, like private, protect, whatnot. They would have to have precise interfaces, very elaborate signatures, and all that stuff. And every single bit of that makes it less simple. So it's going to erode into its simplicity. I do agree that there is a sweet spot in which modeling power and simplicity kind of go together, but if you want to model really precisely things, you're going to have to complicate the language. Thanks. All right, so D does not replace C's memory model, which is a bit surprising because C's memory model is pretty low level. What is C's memory model? How would you characterize it? You know where the crap is, right? You know where stuff is, right? So you know where objects, where things sit in memory, right? You have bit level access if you want to those. You can cast a void start to an integer and back, and nobody is going to beat you to the bro, right? So this approach is to build on top of C's memory model, add structure on top of a loosely structured universe. And by that I mean, essentially, you have the C memory model, which is the rock bed of everything, and on top of that you build the programs which have safety enforced by the compiler that you can occasionally break and go down to C. As a proof, essentially in C, you can use malloc and free if you so want. You can use malloc and free, essentially all of C standard library. You can even use allocate, the non-standard function for allocating stuff on the stack, which is very useful sometimes. D has a garbage collector which is faster but not required for D programs to run. So essentially you can build a D program that does not make any use of garbage collection, but for most applications, of course, you would go with the program and you would allow garbage collection because it's very convenient and very safe. This approach to safety is layered, and what I mean by that is that you can define at design time how safe your program you want to be. And there's 3 levels. One is safe. I'm going to be safe. I'm going to play it safe. I'm going to use the garbage collected memory. I'm never going to cast a pointer to an integer and, God forbid, back. Right? I'm never going to do such stuff, and the compiler enforces that stuff. And the second is trusted. Trusted means I'm a library writer, and I want to break the type system inside the library. However, the interface to my library is safe. What's an example of a trusted function? Trusted. It has to break the type system. However, it offers a safe interface. Alloc. Garbage collector's allocation primitive, right? So the garbage collector is going to inside break the rules quite a bit. It has to make untyped memory look like it's typed, typed memory to look like it's not typed, but outside it's going to be, allocate for me this object. And the garbage collector does have a safe interface. Incidentally, malloc itself could arguably be called safe, but free is not. So there is an asymmetry there, which is rather interesting. All right, now D has there is this all-out war on incorrect programs, and D has a principled, however practical approach to correctness. Well, when I say principled yet practical, I'm saying D does not get too serious about itself when it comes about checking. What happens is that you could be easy erring on the principled side and become all too principled and disallow half of the interesting program to compile. And last but not least, D fosters threading without races. Actually, memory sharing and threading and message passing without races, guaranteed. And I'll give more detail about that in a few minutes. The compilation model is D is a compiler. It generates native code, has context-independent declarations, unlike in C++, where essentially every line of code depends on everything that's above it, right? So in D, essentially every declaration is context-independent, and that has two good consequences. Consequence number one is the top-level declarations are entered in parallel by the compiler and could be actually literally parallelized. So there could be a parallel compiler could be written that compiles every single declaration on a separate core, for example. That hasn't been done yet. We're getting close to that. There's other parallelism in the decompiler that's being used. The human reader doesn't need a lot of context to understand a function, for example. There's minimal context dependence there. And each character is being looked at once, and each symbol is loaded once when you compile a program. Does anyone know how many times a character needs to be looked at by the C++ compiler? So each character in a source file, how many times does the compiler have to look at it? Yes? Depends on how many includes you have. Not quite. So I'm saying a given character in a C program, in a C++ program, how many times does the compiler need to inspect that character? Depends on the compiler. Give me an upper bound and a lower bound. All right, so the upper bound specifies if you implement the compiler by the standard, which has a number of passes, 7 times. So if you go by there are processing steps and whatnot, and if you go through it, it's going to be 7 times you got to look at each character.
You claim that if you have a large tree of includes, the same include may have to be looked at many times, which is one of the reasons why C compilers are so slow.
This is an excellent point. Yes. All right. I completely agree. So if you have many includes, essentially each character needs to be looked at even more, especially if your compiler doesn't have the include guards optimization, all that good stuff. But even without taking includes into account, 7 times would be the upper bound. And the lower bound, the best C++ compiler I know of, looks at each character 3 times. They couldn't bring it down. That's the digital mouse compiler. They couldn't bring it under 3, no matter how hard they tried. So D was engineered, of course, by Walter Bright himself. He got tired of that, so he said, you know what, I'm going to build a language in which each character must be only looked at once. And each symbol needs to be loaded once. D is the fastest language to compile by a large margin of all languages I know. By a very large margin. This is a complete game changer. So what's happening is that essentially it compiles for 2 orders of magnitude faster than C++. And it produces native code. So look at your D program. It's a fairly large program, and you say I'm going to change something, and before you blink, it's being compiled, right? And that's great because it completely changes the way you approach programming. You don't have those. There's that joke with MapReduce and people kind of sorting away, all that good stuff. The original joke in SKCD was about compiling. Oh, we're compiling. The manager's like, oh, okay, yeah, you're compiling. All respect for that. That's not going to be a good game with D, turns out. All right. Let me talk about correctness a bit. So, do you hear me on this? All right. So I was saying that D is very big about correctness. And I think many languages do a very sloppy job at it. Many languages barely allow you to write correct code, and essentially they don't foster it at all. And the least resistant path of writing some code is the incorrect one. So correctness starts with hello world. So this is how the D hello world looks like. This is what it looks like. And there's nothing interesting about it except that it's correct. It is a correct program that does the right thing in all circumstances. To wit, let me ask you this. What is incorrect about C's hello world? This is a C hello world. What's wrong about, yes?
You're missing the return value.
I'm missing the return value. I copied this from the 1978 book on C. It's a verbatim copy. So it's supposed to compile and run. So what's wrong about this program? Yes?
There's no return type given for main.
There's no return type of main. By default, the return type is int in C. That's not the problem. The problem is the following. What happens if the actual printf fails? What if you're trying to redirect the output of printf of hello world to a stale socket? Or to a SSHFS mounted drive that's not there anymore? Or to any file that fails, any output that fails? What's going to return? For that matter, let me ask you this first. What's this program going to return on success? If everything goes well, what's the result code returned to the operating system?
Well, best guess.
Talk to me. Yes?
It's best guess.
Best guess. All right. What's the best guess?
Whatever happens to be.
All right. Talk to me. Well, now, give me a number.
The number of characters in
The number of characters in the string, which is? All right. 13. Quite faithful, I would say. So this program returns to the operating system 13 in case of success. And what does it return on failure? 127. Because printf returns -1, it makes it into whatever register the machine uses for the return value. -1 is going to get truncated. And at the end of the day, you have a program that returns 13 or 127, which is almost like 13 times 10 minus 3, right? So there must be something there, but it's an incorrect program. All right? Let's move on to C++, 20 years of progress. I've been merciful. I've used \n instead of the endl disaster. All right? What does this guy return? Talk to me. Yes?
0.
0. Well, it returns 0 whether things go well or not. It returns 0 on success and returns 0 on failure. Why does it return 0 on failure? It's a bit more complicated. By default, the IO strings do support exceptions, but exceptions are turned off by default. So you have to know a fair amount about this, about the way IO strings work to make hello world correct. Let me repeat: to make hello world correct, not interesting. To make it just kind of do the right thing. Okay? Well, that's a sort of problem. Not to mention that I've never been fond of IO streams. Notice the positive attitude. There's an exclamation mark. So again, I copied this code verbatim from the first edition of the C++ book. You got to learn more quirks like stdc out. What was that shift operator doing there? And more trouble with multi-threaded I/O. What do I mean by that? Why is cout worse for multi-threaded I/O than printf? Oh, hi. Yes. So essentially everything you want to print is going to be a separate call, whereas printf locks the output file once. It outputs everything and then it unlocks the thing, which is incidentally what D does do. All right. So in C++, everything went better than expected. You're going to claim success whether or not it succeeded, actually. All right. So my litmus test for evaluating languages for how serious are they about real, good, production, strong, reliable code is the following. I read the tutorials, and the tutorials are by definition engineered to make the language look good. So the tutorial is like, oh, look how nice you write quicksort. 2 lines, 1 line. Write a one-line quicksort. Evaluating it and seeing how good it is, it's a completely different matter. And then consider various production scenarios. I/O may fail. Input may be very large. API calls may fail. Input may contain non-ASCII characters. So what does it take to take the nice examples and make them ready for production? Right? Oh, that was a demo. No. To write the correct hello world, here's what you have to do, my friend. Right? And to write the correct echo, cat, whatever program, you got to take it through some steps to make it correct. So indeed, there's an all-out war on doing the path of least resistance, do the right thing. And echo is the simplest program that actually does something interesting. Like we all use echo in the in our make files, for example. And the way echo works is it takes this -n. Don't output a new line. This is an option, a -n. So essentially what this guy does is, probably the shortest program that does something useful. And you get the option -n, you pass some configuration options and whatnot, and you write the join of the arguments to the program, followed by an optional new line. My point is that this program is correct. It's correct for the following reasons. If anything weird happens here, this is going to throw an exception. If anything weird happens in the join, it's going to throw an exception. If everything weird happens in write, it's going to throw an exception. The exception goes out of main. The exception is going to have main print an error message to the standard error, and it's going to return a non-zero code. Otherwise, the zero code is going to be returned. And that's the end of it. Now, in the past, people have tried to approach correctness in different ways. So, for example, for design and implementation validation, there's been contract-based programming, all that good stuff with invariants, preconditions, postconditions, right? Who knows about DBC? DBC, design by contract, all that good stuff? All right, I mean, the poster child would be assert, right? Error handling, we are sorry for the typo. We're celebrating a 40-year this year, 40-year anniversary of the movement against checking error and error codes, which is a very strong movement. Nobody checks their error codes apparently. I know you do. I mean, present companies excluded, of course, right? I've ever checked, right? And even for people like you, propagating errors manually is a continuous friction and sand in the eye on an uphill battle in the sand up to the knees and uphill both ways and everything, right? It's a continuous friction that you need to put up with. So then there's been the try catch using unwind protect. Does anyone know what this unwind protect? All right, it's a Lisper's way of doing a try catch and all that good stuff. So I think they're never going to scale. I think it's time to say, you know what, we're abandoning this battle here. And nobody's going to use them properly. Nobody. So let's try, why don't they scale? Because they all affect the normal code path. They have you change the shape of your normal code path. And I think that's a fatal mistake. So now how does D go about it? For design implementation validation, there are full-bore contracts with in, out, and all that good stuff, and built-in unit tests, which make it very easy to write good programs. You just put a unit test there inside your class or outside, and it's going to be run if you pass -unit test to the compiler. When it comes to error handling, D has what I call modern exception handling, which is divorced from the notion that good error handling means a lot of try catch or a lot of try finally, and all that jazz that's going to do transaction code by hand. Indeed, you can throw from anywhere at any time. You can throw from destructors. It does have destructors, so you can implement like C++'s idioms. You can throw from destructors. You can throw from finally. You can throw from anywhere, and the exception is not going to be lost. Yes.
Does anywhere include signal handlers?
Does that include signal handlers? No. I'm sorry. Embarrassing question number 1. All right. the interesting point here is that you don't lose information. So what happens if you throw and the destructor throws and whatever is on the stack there is going to throw again, and you have 1,000 exceptions being thrown? What's going to happen? Well, what's going to happen is the following. Exception, you can't throw any object. You can't throw an int, which I think would be a useless feature anyway. You can only throw throwable objects. And throwable objects have a field called next, which is of type throwable. So throwable implements a singly linked list. It's a closed type. It has the closure property. You can create as many throwables as you want, and you can chain them together. So when you catch an exception, you might be catching a whole chain of them hanging onto the original exception that's been thrown. See what I'm saying? So you catch the exception that was originally thrown, and then you can ask yourself, well, has there been any collateral damage while this exception was in flight, right? And you can actually inspect the whole chain and make decisions. Yes?
What happens when you run out of memory trying to allocate a new throwable?
What happens if you run out of memory if you try to allocate a new throwable? Where is Sean? All right, Sean can give you the answer. Essentially, this is going to be a forceful abort, right?
There's, like C++, there's a standard out-of-memory error instance that's thrown all the time. But as far as chaining is concerned, yeah, that could get ugly, and we'd have to handle it explicitly.
Sean is going to fix his whole code. That was the message, the high-level message that everybody needs to take. All right, embarrassing question number 2 here. Sir. All right, these books are not signed. You may want to come after the talk or not. I mean, depends on what you want to do with it. These books are collector's edition. They don't have the author's name. And, I guarantee within a few short years, they're going to be worth millions. But, of course, I predict that's because of the hyperinflation that's going to happen, right? I mean, bread is going to be like $1 billion, right? All right, so let's actually look at some examples here. Transactional file copy in 9 lines. Of course, I'm going to avail myself of some system functions that are already implemented. But my point is there's no control flow in this function. What I do is the following. I'm saying, I'm going to enforce that I got 3 arguments. Otherwise, the invocation of the program is incorrect. I say, if you didn't pass me program, file 1, file 2, I'm going to abandon execution. Then I'm going to say, you know what? I'm going to allocate a temporary name with the messed up suffix, which is going to be the temporary file that's going to be created as part of the transaction. Then I'm going to say, if the scope fails, if execution within the scope fails, do this. Scope is a statement in D. Do this, and it actually can have here a statement. So you can put an open brace, you can put as much code as you want. If the statement fails, then if the file exists, then remove it to clean up after ourselves. This would be abandoning the transaction. Yes?
What happens if you run 2 instances of this file?
What happens if you run 2 instances?
Yeah, 2 instances of this program in parallel.
What happens if you run 2 instances of this program in parallel? Well, it all boils down to what copy does, right? And copy is implemented std file there. And essentially what copy does, it's going to open the source file with using the POSIX primitive function calls, API calls. And my belief is that that call is not locking the file. So there's no advisory lock placed there. So I presume that the outcome is not going to be very good. Which means you're aiming for the book, I suppose. All right. Thanks for being here. Well, let's talk after this. All right. Yes. Question for the book.
Not sure, but I have a question on the scoping. So obviously copy comes in from, well, not obviously, but appears, as you said, that copy comes in from standard file, and perhaps some stuff comes in from standard exception. What happens if both these libraries find the same
Okay.
identifier?
So the question was, you have these nice names. Copy, exist, remove. Probably another library will want to define the same names, right? So what's going to happen then? This is a short program. It's a script. So name lookup, I want to do the minimal amount of typing to get my job done. However, in D, what happens is D has an anti-hijacking built-in lookup mechanism, which means the following. The call to a function, the semantics of a function call, never depends on the imported modules. So now let's say we import std algorithm, which does define a copy function with different signature. And now we have this ambiguity here. Do you want to copy one string into another, or do you want to copy a file into another? In that case, if and only if the signatures would actually clash, so if the call would be ambiguous, if and only if in that case, the compiler is going to issue a compile time error. The way you fix it is you prefix here std.file.copy, right? And this is a very nice mechanism. I think it's not paranoid at all. So essentially, it signals and it prevents ambiguities only when they risk at arising. Not, you know what, I'm preventing this call because I might be thinking that at some later point in your life, you're going to include another header, another library, and you're going to have an ambiguity. Yes?
Reading this code, how do I find out from which library does copy come?
By reading this code, how do I figure from which library each call comes? That's a question for the book. I'll give you one. So essentially what happens is, at the end of the day, you got to read the fine manual, RTFM, right? So essentially what you're asking is like, why is overloading kind of functioning, right? Why do we have overloading in place and whatnot? Yes?
Also means that if somebody else later changes one of those libraries, may break dependent files. They don't know anything about that.
Yes. Changing the signatures of the functions in one library may break its clients.
No.
All right?
No.
Yes?
Adding a function.
Adding a function to one of the libraries that you import already.
All right, we can handle this. Hold on.
You said not changing the signature, adding a new function with a new signature.
No.
Adding copy to exception.
No, hold on. Give me a minute here. So this is really, really well engineered, I hope. So I have a good answer to this. You're not going to get the book, folks. All right, here's what happens. This resolution of hijacking is at module level, which means if somebody modifies a module, if somebody modifies one module, they are well aware of what else is in that module, right? So if I come later and say, well, I want to define an overload of copy that catches some particular cases of this copy, that's entirely legal. But it's not possible to break the modularity, which would mean I come with a different module from a different universe, and I'm going to define my own copy, which is going to hijack the copy that was initially rightfully owned by that guy. Yes?
No, but what I'm saying is here it's clear that copy, well, it's not clear at all, but apparently copy comes from standard.file.
Yes.
Okay? So you said that if there's another copy that is in standard exception, for instance, that doesn't match this one in terms of full signature, there's no problem. We will just take the one from standard.file. Okay? Now it could be that there's a third library imported that doesn't have a copy at all. Okay? Now somebody comes and adds a copy to that third library down the road, years later, which happens to match exactly this one. And then you have a conflict here in a dependent library that's never had a problem before.
Yes, but I hope you agree that, I'm sorry, let me repeat the point. The point was the following. Well, we have this copy, which is an std file. What if somebody in std exception years later adds a copy, which is going to interfere with this guy, and it's going to break this call upon recompilation, right? I think reasonable people might disagree. I think this is a good behavior. At the end of the day, this is pretty much what I want. No, I think we need to take this offline. I mean, I'm not even halfway through the slides, so let's take this offline. I'm going to give you a book, my friend. Believe me. All right, so just in hope to quench this thing. But I do agree that reasonable people may disagree about how paranoid or how strict you want to be about enforcing visibility. All right, so truth in advertising. I've studied this function a bit, and the control flow in 47 lines of code, which is the body of the entire function, there are only two flow control statements, so one if and one for. And the if handles out of memory. It either succeeds, and this is a mantra that I love, the function must either succeed or fail successfully, right? So it doesn't do anything in between. It makes 6 calls to enforce, has 4 scope statements, and no extra 8. It uses like the very low-level C primitives. It replaces a function that was written sort of old style, which was more than twice as long. It had 9 go-tos to 5 labels, because it used that idiom, whenever anything fails, you're going to jump to the end of the function, right? 9 go-tos to 5 labels and 11 other control flow statements. So I think it's a net win. All right. Question, yes?
May I ask what fail successfully means in copy? Like, what happens if there's a failure in after you copied partial file, like you run out of space in the disk or something like that? How do you fail successfully?
All right, how do we fail successfully? Let's analyze this function a bit. All right, this is going to haunt me forever. All right, fail successfully means the following. So you create this temporary file and you copy it. If the copy itself fails, there's 2 things that might have happened. Somebody pulled the plug on the actual hardware. So while the file was midway through, somebody actually pulled the plug. In that case, you're going to have a file with the .messed up extension on your disk, right? Which I characterize as a successful failure. It's not the target file's name, all right? But if somebody doesn't pull the plug, but it's disk full, what's going to happen? Copy is going to throw an exception. The exception is going to navigate here. When the exception navigates here, this code is going to be executed, and if the function exists, it's going to be removed. So if you don't pull the plug, you don't even get the messed up file, which is good because you were in a disk full situation already, right? If rename fails, well, rename fails. It could fail for a number of reasons, but again, it's going to either fail or not fail. Actually, in Unix, rename is atomic, so this is a good way to do transactional copy. So you either reach this point with success or you end it with a failure. In the case of failure, this file is guaranteed to be removed, right? Yes?
So, you were talking in the next slide about the superiority of D's copy routine. Is that an inherent part of the superiority of the D language, or just because it's a more modern implementation? Could you do an equally good implementation in C++, do you think, or is it actually that D is better?
All right, good question. Well, this kind of has us navigating in treacherous waters here. So here's what I think. I personally think that the scope statement and the style that it fosters is a complete game changer. I think it's impossible to write good code with try and catch. I think it's impossible, next to impossible, practically impossible to write correct transactional code by using try catch. As soon as you have 2, 3, it grows exponentially. If you have 2, 3, 4 atomic actions that each may fail and each must be undone, doing that with try and catch is a disaster. Doing with these structures has the friction of having to define all these new types, of which only reason is to decrement a thing or deallocate something or close something, right? So the way you write transactional code in D is you do action, scope failure, undo. Action, scope failure, undo. So the correctness of the code can be assessed by watching the grass grow. You just look at the linear, it's basic blocks. It's the linear flow of control, and you can write very intricate transactional semantics functions without control flow. So yes, I do believe that. It's a personal belief, which may or may not turn out to be true, but at least for my code, I think it's I've proven to myself that that's the case. Yes.
The scope statement, at least just naively, looks sort of like it's almost a syntactic sugar for try catch. Finally.
Yes. In fact, it's rewritten into try catch statements. You don't want to look at those though. That's the point. So if you have like 3 scope in one function, the equivalent try catch is going to be so convoluted that it's going to be unbearable. So yes, it's a good point. They're really sugar over try and catch, which is, try and catch is like, imagine like before Fortran, people are like, oh, you can't call functions. You got to pass the parameters on the stack. by hand. And everybody's like, okay, I got to do it. You know, what am I going to do? And the Fortran came and said, oh, no, let's make it automatic. This is what scope does. It automates this stuff. All right. What is generic programming? Talk to me. What is, I mean, you know, we hear about it. We know about it. It's something cool.
Compile time parameterization.
Compile time parameterization. Anyone else? Templates. Well, templates are but one solution. What is generic programming? Yes?
It's a way to work with a variable whose type you don't necessarily know.
It's a way to work with a type that you don't necessarily know. All right. I think all these answers are kind of hitting the thing, but not quite the middle of the circle there. So any other? All right. Here's what I think. I think it's very simple. It's a 3-step process. Step number 1 is you find the representation of an algorithm that uses the narrowest requirements possible from the data it operates on. So you sit down and think hard. What does it take for me to be able to revert this thing, or to find something in it, or whatnot, or to sort it? Big O encapsulation should be a crime. I think it has negatively affected this notion that complexity can be encapsulated away as an implementation detail. I think it's been a huge hindrance to a whole generation of programmers. I'm not going to say what language fostered that. Low-level efficiency is also important because it reduces the impetus of people to actually sit down and write their own implementation by hand for speed reasons. So that's step number 1. Step number 2 is you define types that implement said requirements. Step number 3, you leverage the algorithm for ultimate reuse. Because you get to reuse it, since it was defined on a very narrow interface, you get to reuse it with a lot of stuff. And of course, at the end of the day, you're going to allegedly profit. I think it's, for my money, this is one of the best thing you can spend time on. Why? Because programming has so many aspects. It's a social thing. It's an engineering thing. It's many things. But at the end of the day, it's a math thing. It's a science. So you got to do what the scientific method has you do, which is look at algorithms and devise how they should be working on at their best and reuse them at their best. Here's an example. Let me actually jump to the example. Simplest example is the min function. It's very difficult to define correctly because it just has 2 types here. There's a collision there. Here's how you define a correct min in D that is as good as a min you wrote by hand, and it features the following. By the way, do you know why I put, min? People say, when they define min, people usually say left-hand side less than right-hand side. Why do I reverse the 2? Stability. Okay, explain.
If the 2 are equal, then you want the left-hand one because you're going to use this as a primitive in other algorithms, and you're not going to want to shuffle the order unless you have to.
Awesome, thanks, Matt. Okay, so Matt's answer was, well, what you want to do is kind of decide that one thing is lower, kind of swap the things, choose the right-hand thing, only if it's actually greater, if it's actually smaller. Otherwise, you want to leave the first thing in place. So in case of equality, you want to kind of keep LHS. So now, this is sort of a little detail that the C++ community took many years to grasp. Yes?
So in this example, L and R are your type parameters, correct?
Yes.
Where do you say that these type parameters have to have a less than operation?
Good question. So the question is, L and R are type parameters. And the question was, where do you say that there is a constraint on L and R that there's 2 constraints, actually. Constraint number 1 is that you need to say LHS, this comparison works and returns a Boolean. And the second requirement is? Yeah, so essentially, these guys must have a common type. They must be, there must be an intersection that's non-void between these 2 types, so I can return it. Now, the trick is, this is a concepts kind of question, and it's a bit embarrassing because I don't have this on my slide. I thought I would save slide real estate. Let's see what we can do here. Okay, let's see. In the interest of time, I'm going to declare myself embarrassed because what I could have done, copy of the book for you, copy of the book in the back for the gentleman with the beard. Please see me. All right. So copy of the book for you. Actually, let me pass it back. All right. So what happens here is the following. You could add here an if clause that says, if LNR, LHS less than LHS returns the type bool. So D has that capability. And then you can say there is a common type of RHS and LHS. Or you could say if this whole expression compiles. And the whole banana comes in between the close parenthesis here and the open brace here. Now I'm ashamed that I didn't put that code on the slide. I wanted to save some slide real estate. But you can see that in the numerous examples that I gave in articles and elsewhere. So essentially, it's very easy to add constraints to generic functions. All right, so pass this back. I'm going to give you one more. Question? Good question. So what's the return type of value or reference? Again, I'm guilty of simplifying a bit things. If you put autoref here, and you put autoref here, and you put autoref here, you get the reference thing. That's all you need to change. There's no other, there's nothing up my sleeve. But that being said, I think going with values is fine. I've been thinking for a long time, when do I want to say min of A and B plus plus? Right, because of that L value, that's what you want, right? So probably not very often. So, all right. By the way, I have only one copy left, so you gotta really embarrass me here to give it to you. All right, well, compared with the C++ implementation, which already is incorrect for a number of reasons, but anyway, it's not incorrect, it's incomplete. Anyway, so Matt, have you heard of this guy? All right. So somebody sat down, Howard Hinant actually, sat down and wrote the correct min in C++. The right min. And it takes 175 lines, 10 types, and 12 specializations, and does the right thing. All right? And that was rejected, unfortunately. People thought it's just too much aggravation. All right. Iterators versus ranges. D defines ranges as a primitive, not iterators. Why? Because iterators, while they're very useful and flexible, they're fundamentally uncheckable. If all you have is one iterator, there's nothing you can assert about it. What you have to do is have two iterators and assert a relationship between them. So what I did in D essentially is I encapsulated both, and I made a primitive called range, which does not expose the iterators. It exposes its own primitives. Then I define a superset of STL on top of ranges. I suggest you, if you're interested in, just Google for on iteration, which is an article, or std.algorithm, which is this standard algorithm implementation. And it turns out ranges have proven to be a treasure trove. They pervade I/O. They pervade D. It's I/O lazy evaluation. Even random numbers you get as a stream as a range. Yes.
So you could have done ranges in C++ as well. I mean, this is a library thing.
You could have done ranges in C++ as well. There's a library thing. Yes, I agree. People have not done it, though. But actually, this is a good point because I define ranges to generalize these arrays, built-in arrays, which are actually, there are a specialization of ranges. C++ does not have an array primitive, and therefore the train of thought didn't go that way. It's a good point. Not embarrassing enough. All right. Containers. This approach is there's no container hierarchy. I think that's the right approach. There are containers, there's no hierarchy. Why no hierarchy? Who here knows about Bloom filters? Bloom filters. All right. All right. Tell me, what's the super type of a Bloom filter? Okay, what are the primitives of a Bloom filter? Talk to me. Of the people who rose their hand, come on. Yes?
It's a set, but it's a superset of what you put into it.
what would be the primitives that you would define for a blue filter type?
Insert.
Insert.
Contains.
May contain.
Yeah.
Right. Almost sure contains. You know, right. I'm pretty sure it contains and well, there is one more, like create the total universe, because in Bloom filter, you can, if you assign all bits to 1, essentially create the total universe there, the whole set of types, everything is going to be in there, which is very particular. So anyway, so Bloom filter has insert at almost sure contains. How do you iterate a Bloom filter? It's not, don't even think about it, right? All right, let's, something more. Who knows about tree, T-R-I-E? Try, some say try. All right, what are the primitives of a try? Can you integrate a try within STL? Or within Java collection library, or within C# humongous collection library? You can't. You can't even if you wanted. You can't. So D says, you know what? Let them be free. There's a freedom. They could abide to certain named interfaces, which is, if you define insert, then it's assumed to have certain semantics for a container, right, including complexity. But other than that, there's no relationship between them. Some containers indeed have stable insert. What do you think stable insert does? Stable insert, stable remove. What do you think the stable thing does? Compared to STL, insert, remove, erase, erase, yeah.
Doesn't reorder equal elements.
Almost there. What's a liability in STL's insert for containers? Different across different container types.
Invalidates.
Iterator invalidation. Stable insert does not invalidate iterators. If you can insert without invalidating, you define it. Otherwise, you don't define it. And code could use introspection to decide what to do, whether or not your container has this capability. See my point? So a container may define insert, which does not make any particular guarantee. It may also define stable insert, which could be an alias to insert, by the way. It's a one-liner, just an alias. There's no overhead. The alias two names together to mean the same thing. And then what you do, your users are going to be like, oh, does this guy support stable insert? Then I can implement this cool algorithm. Otherwise, I'm going to go conservative. All right? All right, I have an upcoming article which is called Sealed Containers and shows how you can implement containers that use malloc and free for deterministic deallocation while at the same time staying safe. It's a trickier thing that I might have thought, so I recommend you stay tuned. Who knows about edit distance? Levenstein. Right, edit distance between two strings tells me how much do I need to modify one string to get the other, right? So it tells me like spell checking, all that good stuff. Now there's this algorithm, Levenstein created it, I think probably back in the 30s or so. And it's not simple, it's a dynamic programming algorithm. So what I define here is a generic function that takes Levenstein, that takes an equals function which may be expressed as a string with the convention that A is the first argument and B is the first argument. This is the easiest way to define a short lambda in D. You can actually define an actual function there. R1 and R2 are the inputs, and I impose the constraint that both are forward ranges. Now here's the trick. Usually, if you Google for, well, this is a sort of a, if you Google for Levenstein, you're going to see that the usual assumptions are the strict equality imposed there, and that the inputs must offer random access. Everybody in this world and their brother implement Levenstein on arrays, not on lists. I'll tell you why this is very important. Why do you think this is important? Arrays, not lists. Why do we want Levenstein to work on lists? On forward iterators. All right, next slide is going to tell you. All right, UTF encoded strings. They're not arrays. UTF-8 strings are not arrays. They are ostensibly arrays. They are defined as arrays in D. I say, you know what, I'm taking an array of immutable characters, and I call that a string, and I call it a day. So each character inside the string is not modifiable, but the string can be rebound. So that's why that syntax over there, right? So this is what is defined somewhere in the guts of the standard library, okay? Now, formally, string and WString only offer bidirectional interface. Why is it bidirectional? Because in UTF, it turns out that you can go from both directions, no problem. You can't have random access because it's variable length encoding, right? UTF, Unicode, right? Unicode encoding, okay. So in strings, you can't go like, they don't have an indexing operator. These guys offer it because their alma mater is actually an array. However, formally, they don't claim they have random access. So an algorithm that says is forward range is not going to, it's going to work with strings, but if it says it's random range, it's not going to accept a string. Now, here's the trick. The net consequence of all this is that the Levenstein distance function that I defined for D is the only function in the world that fulfills the following. Works for all strings, works with custom comparison, and there's no copying going on. There is a function in Python that does work correctly on UTF strings. It makes a copy in dchars, like 4-character, right, to have random access. Now, very interestingly, Haskell lists, right? Haskell lists. I went to Google Code. I was very surprised. So Haskell has 4 implementation of Levenstein. 4. 3 of them use arrays. In the language that put the L in list, well, list put the name in list, but Haskell is using list through and through, right? So in the language that uses lists, everywhere, there are 4 implementations of Levenstein, 3 of which require arrays, require indexing. The 4th does not use dynamic programming, it's a big slow. There's no good function, there's no good Levenstein in Haskell. Why is there no good Levenstein? Because nobody thought generic. Nobody thought, what does it take for Levenstein to impose the minimum on its input? Everybody goes to Wikipedia, reads the Wikipedia entry, looks at there's a random access here, I better use random access, and they call it a day. No, Levenstein works on forward ranges. Interesting enough, it doesn't work on files. Who here knows about Boyer-Moore? Fast string searching. Boyer-Moore is an algorithm that allows you to quickly search a large string inside a large string for a smaller string. Very fast. It's sublinear fast. Sublinear. We're talking quadratic versus sublinear. So, wow, I better get on that bandwagon, right? Boyer-Moore, I discovered, it just so happened, I thought of it for a long time. I discovered that Boyer-Moore works in a limited form if one of the strings is a bidirectional array, bidirectional range. It works. It's a bit restricted. It works pretty well, right? Do you think this is important? Raise your hand if you think this is important. All right, nobody. It's like, nah, whatever. All right. I think this is important. I think it's important that I sit down and say, you know what? Boyer-Moore works for Unicode strings without making a copy. Whoa, that's pretty cool. I mean, I do want to be there, right? If I'm interested in fast string searching and I want to be UTF correct, I want this. I'm interested. The same goes about many other algorithms. I don't have the time to discuss here. All right. We have 1 minute for the rest of my talk, but I can't stand not telling you about this. Factorial function. All right. A nice compile time template factorial function, right? Which was it was a huge event in the C++ community. It was one of the first instances of compile time program that computed something interesting, right? There's actually one before that computed, I think, prime numbers, but it wrote them on the standard error in form of the compiler error messages, so that was not very useful. Factorial was borderline more useful. All right. Forget what you just saw, because indeed you can do the following. You can write a factorial function like a normal function, and later on you can say, I define an enum, which is a statically computed value, to be an expression that normally would be runtime evaluated. By asking for an enum here, that's enough for the compiler to go ahead, interpret factorial during compilation, and replace the call with the result. Yes? Can you do that for functions that ask for I/O? That's not embarrassing enough. So I'm not going to give you the book. I have one more copy of the book. I remind you. So the answer to that is the following. Certain functions and certain primitives are not compile time. They can't be evaluated during compilation. A call such as write or write line or printf or whatnot the compiler is going to choke on it. It's going to say, I'm not going to compile this. So the answer is no, you can't do I/O that way. You can. There is a pragma that does output and stuff. Yes?
So does the compiler figure that out dynamically or statically?
Dynamically or statically?
So
okay.
The compiler could crash while evaluating.
Good question. Excellent question. There's been a very recent discussion on actually enforcing this statically. It turns out it's conservative. Doing it non-conservatively is a halting problem. Essentially, to figure out if I'm going to be able to evaluate this, tantamount to actually evaluating it, trying it and see. Am I going to sit here for 2 days compiling, or what's going to happen? Yes.
Slowest compile ever.
Come again?
I can still make this as per program to compile the slowest ever.
Yes, you can. You can make the slowest to compile program. However, I remind you that the decompiler is the fastest compiler of any compile language on Earth, and probably solar system and a few other planets. Yes?
Well, I disagree with that, but still.
Why do you disagree?
Because technology of compiling by looking at one character, each character only one time, and doing that kind of stuff is all old technology. It's been done for Pascal, it's done for Model 2, it's been done for many other languages.
Right. So why does decompile 100 times faster than C and 4.5 times faster than Go? I tell you why. It loads files asynchronously. It does I/O, and also it can, that's not exploited, but it could enter all declarations in parallel. But let's save that for another day, because we're running out of time. I hope this is cool. You can actually, as the compiler, you're gonna say, I have this function, I want it evaluated during compilation and save my time during runtime. Now here's the trick. There are limitations. You can't call malloc during compilation, right? You couldn't if you wanted, yes?
What happens when factorial then uses a compile time constant? Are you getting into loops or something?
You are liable to get into loops, but not with that scenario. That's a simple scenario that the compiler can take care of. But of course, if you have a recursion running amok and everything, the compiler is going to simply choke on it. So essentially, it's going to blow through and try to evaluate everything. It's going to choke at system calls, malloc, new, casts, any unsafe thing not during compilation. You can't give me a D program that's going to ruin my system during compilation, right? And such stuff. All right. So this is the last thing I wanted to share with you. And who has a 12 o'clock? All right. Who can sit here for 10 more minutes? All right. Perfect. Thank you. So I can't stand myself. I want to talk to you about this. And due to these questions here, embarrassing questions about copy being overloaded and all that stuff, I wasted some time. So I hope you give me some credit here. All right. Today, concurrent programming. Several competing approaches. So there's share-intensive approach, which means you start a thread, it sees all the memory. We have message passing like the CSP or actor models, which are pretty old but are getting resurrected today. PGAS, who knows about PGAS? Partition Global Address Space for scientific computing, matrix multiplication, all that good jazz, right? For HPC. There's no definitive solution at this time, but a key trend is that on your machines, passing messages becomes faster and more scalable than using shared memory. Shared memory is an illusion that's increasingly expensive to maintain. As the cache hierarchies are getting so deep that essentially your illusion that you write a value and somebody else reads it must go through all the way up the hierarchy and then go back all the way back to their cache hierarchy. So it's a disaster. Traditional languages were developed in the days when share was cheap and easy. The zero states memory, remember? And again, people all like me remember zero-weight states. You could buy that, right? So they placed a bet on shared memory. D places a bet on message passing and hedges that bet with explicit sharing. And here's how it works. Basic tenet. There's no sharing by default. You can share on demand. Sharing is controlled by the compiler. Here's how it works. If you define a thread local, it's going to be thread. This is global space, right? If I say shared in global, then it's going to be shared, right? Somebody else can modify it. What is the practical consequence of defining this in shared? Like in terms of code generation? Code generation for shared stuff?
You have to get the memory model stuff right.
You got to get the memory model stuff right. What does that entail? Locks? Probably that's too heavy for an int. Cas, talk to me. Come on, memory barriers. Come on, folks. Fences, memory barriers. You got to protect this access from any thread with the appropriate memory barriers. You know, whenever they read it and whenever they write it, and it depends on the architecture exactly how you do it, right? So there's a complicated stuff, but since the compiler knows about shared, it essentially takes care of that. Key points. Shared is transitive. What does transitive mean? Transitive qualifier. If I make if you have a pointer that's shared, everything can reach through starting from that guy is going to be shared as well. Why? Because the thread could do it. It's a consequence, it's not a decision. People were like, oh, why is shared, why did you define the language this way? We didn't define this way, we discovered it was that way. Shared is transitive, immutable is transitive. You can't start from immutable and then go back to mutable. If you start immutable, you stay immutable. Yes?
Does that mean if you have an immutable list, the members of that list are immutable as well?
Yes, if you have an immutable list, all members of that list are by necessity immutable. You can't have an immutable island and then go out of that island into mutable territory. Why is this all geographical reference? Yes?
So you'd said earlier at the start of the talk that you had various different levels of sort of safety you could have in D, in terms of type checking and that kind of thing, and how the malloc could break that. Can you break the shared and immutable stuff in different modules, or?
All right, I'm standing here. I'm saying you can break all of these qualifiers with a cast. All right, that's greppable, but the point is, it's not only greppable, but the point is, if you qualify your code with the safe label, at safe, then essentially the compiler is going to not allow that cast to happen at all. So it's going to choke during compilation. So you can break all of this stuff. And actually, let me point out the following. Here's how the offer is layered. Flagship approach. We have isolated threads, asynchronous messages. Safe modular maintainable, easy to understand programs. Even automatically checkable in the future, I'm sure. Shared variables, log-free code, old school critical sections. You can do that if you so want. Non-safe code may use cast, exactly your question. ASM statements, assembler statements, you can go down to assembler level if you don't like it, if you don't like all of the above. And well, you can use a soldering iron if you so want, but it's not included with the download. Why is this good? Because we know that message passing works. So essentially, in Unix, all the time we use pipes for fun and profit. How many times did you have a pipe that had a sharing problem, right? It could. I mean, if you write to a file and the other guy is reading the file, and it could happen, but it's very rare. So we have the process level concurrency, which works, but it's pretty heavyweight. Inside the language, what D offers is thread level concurrency with shared memory, which would be fast but fraught with parallel. So what D offers, sorry, the D doesn't offer that. What D offers is type system level isolation, which is at the same time safe, robust, and lightweight. So in D, a thread is pretty much like a process from a memory sharing perspective, except that it's lightweight. Make sense? All right. All right, to conclude, well, I have this dog and pony show thing. So what would be the answer to these 3 questions? I don't know what the answer is, but I think the answer is a weighted average of everything that you want, and this is what D aims to be, a weighted average of good things that doesn't fall into any extreme. And I think it has succeeded at that. Questions? Yes?
The separation of memory within different threads.
All right, start again.
Okay. I had a question regarding your previous slide regarding the separation of memory for different threads. So this is completely statically enforced or checked? It is completely statically checked that one thread cannot access.
Yes, it is completely statically checked. Now, here's the thing. The static checks are not going to catch all patterns. So if you're trying to do old school coding with the shared qualifier, many patterns are not going to compile. It's conservative. All right? So what I'm saying here, it's harsh, but it's for your own benefit. Right? If you do need to use such a pattern, you can cast shared away and use the raw access. But the nice thing is that those are hopefully very few places in which you need to do that. So it's easy to verify that code by hand.
So how do I know as a programmer which patterns are usable and which ones aren't? And are they going to change over time?
You buy a copy of this book. I'm sorry, this is like really whoring here. All right, so questions for the book. Could you pass the microphone?
In the compile time evaluation slide, you said that you could evaluate factorial of 10. Any optimizing compiler will evaluate factorial of 10. I didn't get the point. What was so special about D in this respect?
An optimizing compiler could optimize certain expressions, but at the type system level, it's going to disallow initializing a statically computed value with a dynamically computed expression. So if I say the first statement, auto f1 equals factorial of 10, the compiler may as well, if it's smart, decide, you know what, I'm going to evaluate this right now. And I'm going to make it a virtual constant, right? But at the type system level, the compiler is going to say, if it sees enum f2, the language definition must be like, well, you know what? Here I need to make a decision. What's a constant? And in D, it turns out a constant can be an expression. So it's not an optimization thing. It's a language definition thing. They are different. Matt.
You're obviously at least somewhat familiar with the Go language. Would you like to make any comparisons of the design goals? I'm done.
All right. So any comparison of the design goals of D versus Go. I have to confess, I've been preparing for this really like a horny teenager for the prom night. So I've been learning a lot about Go, and I concluded the following. I'm so biased, I'm not going to say anything. It's useless. I mean, really, I'm very biased, because if I would prefer Go, I would have done for D what I did, you know, what Go is done, because it hasn't done anything like really new, right? So the thing is, I'm not going to say anything. If you can ask me about specifics where I can actually talk about, you know, technical things.
Hi. I had another question about the safety mechanism. What happens if you link safe and unsafe modules into the same executable? Do the unsafe modules have the option of corrupting data or pointers that they get from the safe ones, or is there a protection against that?
This is a great question. So what if you link safe and unsafe code within the same executable? The mechanism is conservative. The way it works is if a safe function tries to call an unsafe function, disallowed. So there's no way to untaint whatever unsafe functions do, because you can't predict what's going to happen. So I think that's reasonable. I think more could be done about it, and I think it's all going to depend on how people are going to want to use the language. Question for the book. Yes?
Do you feel... Sorry.
given the inertia behind existing languages like Java and C++, do you feel honestly optimistic that this has a chance of really replacing just based on technical merits?
It's a great question. Again, I'm biased, so essentially, the markets will decide. There have been languages that have succeeded on merit alone, like Python. So Python essentially had, not a lot of formal support in the beginning. I do think this merit puts it ahead of essentially all languages I know. To be, again, I'm biased, but to be brutally honest, that's what I think happens. Now, the D-book has been out only for a couple of months, and it's the dog days of the summer. It's had good sales already. I think there's a lot of pent-up excitement going on right now in the D nascent, growing community. So I'm optimistic, but I'm cautiously so because you never know how people are going to react to the introduction of a new programming language. It's a good question. You know what? It's a question for the book. Last question. I gave the book already, so it's like, oh, whatever. Yes.
So from a software engineering perspective, I really like the idea of separating the shared state and the non-shared state. But from a performance point of view, I'd like to point out that the CAS operation, which is sort of the fundamental primitive for writing concurrent code with shared memory, is getting surprisingly cheaper. So something that used to take 100 cycles, best case is now the hardware people are doing it so that it's like 10 cycles best case, and so the performance story might not be quite as clear as you made it out to be.
I think I exaggerated a bit in one direction, and let me actually amend that. D has CAS as a compiler primitive. D defines CAS. What kind of pointers do you think CAS works on? Shared. CAS works obviously with shared data. You can CAS things. And actually, D is one of the languages that make it easiest to write lock-free programming with CAS. Easiest. Because you have shared, you have the CAS primitive, and you are safe. So actually, I was very happy that I'm a huge CAS guy. I'm absolutely huge. I wrote a couple of articles about it. I'm not sure if anybody knows, but everybody cares. So I'm a huge CAS guy, and I think CAS and transactional memory are all of the more complex and the better models that people are talking about. I think it has a lot of potential there. So let me amend what I said about message passing being the only the foremost flagship approach to concurrency in D. D welcomes CAS, and it has built-in support for it. After last question. All right, going once. Yes.
How do you deal with memory management if it supports CAS? Do you rely on the garbage collector? Or?
Aha, great question. So what do you do? So CAS code and garbage collection are the best marriage in the world. Agree? CAS is a 5 slides presentation about CAS is a 5 slides presentation if you have garbage collection. If you don't, it's a 35 slides pages, right? Presentation. I gave both, so I know. I said at some point I stopped and I said, if you do CAS in Java, you can leave now. Essentially, this is it. And then it counts all the memory management and all that good stuff. So, answer. It's going to be exceedingly easy to use CAS with the garbage collector in D. It's going to be probably almost as complicated as it is in C to do manual memory management. The algorithms and the underlying patterns are going to have to be the same. You're going to have to cast things away and all that stuff. Yes?
Regarding garbage collection, can you talk a little bit about it? Can you talk a little bit about the garbage collection schemes? And maybe also about the allocation of stacks for the threads?
Excellent questions. All right. So what's the deal with the garbage collector in D, and what's the deal with stack allocation for multiple threads? So as far as garbage collection goes, essentially D has a run-of-the-mill garbage collector right now, which is an adequate garbage collector. It's not the best of the breed, and I'll tell you exactly why it's not the best of the breed. It's because D produces less garbage than other typical programs, right? So there's less garbage. We have fewer men on the task there to collect the garbage. So obviously, that's the dynamics that that's happening. Now, garbage collection could and should be improved, but D makes takes a very strong stance on separating what's garbage collected from what's scoped allocated, like structs. Like in D, a class is always garbage collected, and a struct is always not garbage collected, right? So that's the way it works. Essentially, there's a clear separation. I'm going to use the garbage collected heap now, but I can actually use the stack for structs, which have destructors, hence the C++ patterns, which are great. And then we can use malloc if you so want. And actually, I started using malloc inside my collection library because it turns out garbage collection, it does require more memory to run properly. There have been studies, there's been everything, and essentially the takeaway of the garbage collection studies is the typical program is going to occupy 3 times as much memory to run properly. Right? It could be better, actually, to have garbage collected stuff. It's going to occupy 3 times more memory. The working set is going to be bigger. And that's a consistent result. It's between 2 and 5, but the average is 3. Now, getting to your second question, which was the stacks for multi-threaded programs. D does not have a strong, doesn't have the segmented stack that Go has. My personal opinion, 64-bit are going to make this a non-issue. 64-bit. You know what 64-bit addressing means? It means you always have address space. The people have done kind of similar calculations. Essentially, it takes you hundreds of years to fill the memory. If you have like 64-bit, it takes you hundreds of years. What I'm saying, 64-bit address space means you always have addresses. You always have chunks of memory. Yes, you're going to counter that. You're going to destroy me.
What about the mapping of threads? Are they mapped to OS threads? And if so, what if the OS doesn't provide you with enough threads?
Well, I don't have a good answer to that. Essentially, right now I can say the following. There are weaknesses in the way 32-bit threading is addressed. And from here on, it's an implementation thing. I don't think it's a principal thing, and that's what really matters at this point. Excellent questions. Yes?
Does D have runtime typing information and reflection like Java? If not, how does garbage collection work?
Yes, D has runtime type information, but most interesting, it has static type information. Actually, people can do things like, I was just talking right now with Kirk. So essentially, people can say, give me an interface, and I'm going to define a class for you that implements all of the members of the interface to throw. Mock up for the win, right? So I have this class with this interface with a humongous number of functions, and then I say, instantiate this template is going to implement everything statically to throw. And then I'm going to say, yeah, from this I'm deriving my own class, which implements 5, because that's what I care about. So I can test and play with it. So people are doing increasingly this kind of statically enabled reflection. Dynamic reflection is not as powerful as Java's or C Sharp's, but I think static is the important thing, and the dynamic is a library implementation thing. All right, I'm seeing people kind of getting antsy here. So absolute last question. Absolute last question. Don't leave me like hanging like this. This is prom night. Come on. All right. Yes. Absolute last question. Absolute last question. All right. Thank you.
Biggest app currently written in D. What is the biggest application currently written in D?
What is the biggest application written currently in D? I haven't taken a tally. Walter told me that a lot of people working at actual companies that endorse D contact him and essentially do use D. Companies don't advertise it as much yet. So this is sort of it's unfalsifiable affirmation, so it's not very valuable. A large D application might be the Qt binding for D. So Qt is a huge library, and people have written a binding for it. There are a few sites that have D. D is big on games. Gamers love D, so there are a few pretty big games written in D exclusively. So I'm hopeful there. Again, the book has just come out, and my hope is that now is the inflection point. All right. Well, with this, I'm going to have to end, and thank you very much for sitting here. Thank you.